Hi, I'm Daniel, and today we are going to discuss biomass integrated gasification. First, we are going to introduce the concept of gasification of biomass, which are the types of gasifiers and the parameters that are necessary for simulating this type of industrial process. Finally, we are going to present some examples of the process integration in the industry, such as the fuels production. Let's start by introducing the gasification process as a thermochemical process that converts the carbonaceous material, such as biomass, into a gas that we know as synthesis gas, or in its shortened version, syngas. The feed material is mixed either with oxygen, air, or steam that we call gasifying agents that leads to a series of chemical reactions that convert this feedstock into syngas and ashes that are the mineral resources. As you can see here in the figure, the lignocellulose material is decomposed in volatiles, in condensables, and in other solid materials because they are important for generating heat and power, such as in steam cycles or using the syngas in internal combustion engines, for producing chemicals such as the Fischer-Tropsch liquids, methanol, hydrogen, dimethyl ether, or synthetic natural gas, and the biochemical fermentation in which we are using the syngas or other components that are derived from the gasification to produce biofuels, biochemicals, and biomaterials. In the gasification reactions, we can identify four main steps, in which the biomass is first dry between 150 and 200 Celsius, where the moisture content is removed from the carbonaceous material and is sent to the pyrolysis zone. There, the decomposition of the biomass that is already dry into volatile gases and char occurs. Afterwards, we have a conversion zone where we have a partial oxidation of the char and the gases that have been produced. Then we have the reduction zone, where the gases that have been produced during the pyrolysis process are reacting with the oxygen, reacting with the steam, and then it produces other gases that in the reduction zone finally constitute what we call the syngas. Other key reactions that occur in the gasifier are the boudoir reaction, the water-gas shift reaction, and the methanation reaction. As we can see, the oxidation zone provides the heat to the other endothermic stages, and then in the end, we have a production of ash that is a residue that melts at very high temperatures. Therefore, depending on the temperature of the oxidation zone, it may leave the gasifier in the form of slag or in the form of solid ash. Different types of gasifiers are available. The fixed bed gasifiers, plasma gasifiers, entrained flow gasifiers, and fluidized bed gasifiers. In the case of the fixed bed gasifiers that can be updraft, downdraft, or cross-draft gasifier, the biomass is fed in the top of the gasifier, and then it goes down through the different steps of the gasification process that we mentioned: pyrolysis, drying, pyrolysis, reduction, combustion, and finally the ash separation. Depending on the type of gasifier, updraft, downdraft, or crossdraft, the air, the gasifying agent that is entering my gasifier, can go in co-current or counter-current or cross-current to the biomass that is fed to the gasifier. In the case of the plasma gasifier, the biomass is put in contact with a very high torch of plasma that decomposes, it's a thermolysis of the biomass and decomposes it into the syngas. In the case of the entrained flow gasifier, we feed the feedstock composed of the biomass, but also steam and oxygen at very high pressures and temperatures, and then we produce syngas that is quenched in a quenching water, and finally, due to the high temperatures that are achieved in the entrained flow gasifier, the slag the ashes are recuperated in the form of slag. Finally, in the fluidized bed gasifier, we can have the bubbling bed gasifier, in which, as the name implies, we are bubbling the biomass by using the injection of the air or the steam or other gasifying agent to produce the syngas. In the case of the circulating bed gasifier, we have two columns, in which in one we inject the biomass that produces char, and this char is sent to a twin column where the char is combusted with air or oxygen so that it produces flue gases that are released through the stack. But then this flue gas is produced separately from the syngas. Why? Because in the second column, where we are producing this heat by means of the combustion of the char, we are also sending sand. And this sand is recirculated to the gasification column to preheat the material and then promote the reactions of the gasification. That's why the circulated bed gasifier, that we are going to explain further in the other slides, we have not the dilution of the syngas with the combustion gases. Let's discuss some process parameters, but before, let's talk about the biomass preparation. So gasification is well suited for lignocellulosic biomass. For instance, wood chips, sawdust, forestry residues, if they are processed like bark, branches, and leaves, energy crops, agricultural residues, but some of them require a very stringent pretreatment, like the drying until 10% of water content, chipping, and grinding. The particle size can achieve values as low as 1 millimeter. This is because it's easier for the fluidization of the material. The moisture content, if we compare it with the normal moisture content of woody biomass, that is around 40%, it needs to be reduced to avoid the clogging in the feeding of the biomass. The high ash content may also lead to slagging issues, and then it needs to be treated by considering different equipment for removing the ash in an efficient way. Here you have at the right top a diagram that shows the chipping, in which biomass is conveyed into a system that reduces the size, and then afterwards in the discharge conveyor, that is, it could be a screw, is sent into the gasifier, and depending on the pressure of the gasifier, this could be a pressurized screw or a simpler atmospheric conveyor. In the case of the dryers, we can have different types of dryers: the rotary drum, the flash, or the fluidized bed. Let's explain a little bit more about the rotary drum. In the case of the rotary drum, you have biomass that enters in countercurrent with a hot gas. It can be also steam tubes that preheat the biomass, and then when it's heated above the 120 Celsius, it releases the inherent amount of moisture, reducing it up to values of 10%. In the other type of dryers, in the flash dryer, basically the principle is adding biomass together with some of the drying agents, in this case hot air, and in the end we obtain a drying product that is separated in a cyclone. In the fluidized bed, we put in contact the biomass together with the hot air, and as the name implies, we fluidize this biomass material, and then we remove the moisture and separate the particles in a cyclone. Here we have a diagram of a dual bed gasifier that we are going to use for the discussion that continue in these slides. In this type of gasifier, there are two columns. One is the reduction column, and the other is the combustion column. As it has been briefly explained before, the biomass, it needs to be dried, and this drying could be partially done by using the hot gases that are recirculated from the gasifier. Other ways of drying the biomass, it could be using heat pumps or using another waste heat released from the nearby stack gas. The biomass is sent to a silo, a storage system that feeds the reduction column, in which the biomass is gasified by bubbling it using steam as gasifying agent. The syngas is then removed from the top, separating the particles that go into a sand and char combustion, and then this syngas is sent to the waste heat recovery, and then the screwer for obtaining a produced gas. We say that the char is sent together with the sand, that is the energy carrying material between the two beds, and then here the combustion, it can be achieved by using air, because we are not diluting the syngas that we are producing in the gasifier with the flue gas that we are producing in the combustor. Then in the combustor, we can separate the two particulates, the ones that are basically lighter and the ones that are heavier, like the sand, that goes back to give back the heat to the gasifier column. You can also see that the ashes can be collected and then they can be landfilled or they can be repurposed. Here, this system is well known because it allows to have a fast recirculation and a higher yield of carbon monoxide. It's also recognized because it's a dual bed system operating at atmospheric pressure. The char that is transferred is burned, and then in this case, we are able to obtain a syngas that it has a higher calorific value, around 14 megajoule per kilogram of syngas. The heat is then supplied by using this recirculated sand, but in other cases, it could be also partially supplied by using the Joule effect and using some heaters, especially when the system is going to start up. The flue gases, they can be also post-treated. So when they are released, they can be sent to a carbon capture unit. If we would like to get these additional CO2 emissions sequestered and then mitigating the total emissions of my gasification system. The steam that needs to be injected as a gasifying agent, it can be produced by recovering partially the waste heat out of the syngas cooling. Then this raw syngas that contains some traces of tar, it needs to be purified. That's why we need the scrubber. The wastewater, it can be later on treated, and depending on the composition, it can be also recovered some of the oils and the condensables that are incorporated in this body of water. Here we show the characterization of the biomass and the syngas composition. Here we are going to use an example for sugarcane bagasse, that is a lignocellulosic material, and we see there are two ways of defining the biomass composition. In the case of the ultanol composition, we define which is the mass fraction of carbon, hydrogen, oxygen, nitrogen, sulfur, as well as ash in a dry basis. In the case of the proxanol composition, we characterize the moisture, the fixed carbon, the volatiles, and the ashes that are present in the biomass. In this way, when we are going to simulate biomass gasification, we can perform atomic balances, and then in this way we can determine as well, by using some correlations, how much of the syngas is produced, and also which is the composition of this syngas. As you can see here in the right, the composition of the syngas can be 30% of carbon monoxide, 10% of carbon dioxide, 34% of hydrogen, almost 40% of water, some traces of nitrogen, hydrogen sulfide, and ammonia, and there is a certain amount of content of methane. It's important to see that the quantity of nitrogen that is included in the syngas is very low, thanks to the utilization of the dual bed gasifier that we have described in the previous slides. In the gasifier, we have certain demands of energy required to prepare the biomass and also to supply the gasifying agent and preheat the streams that are going into the gasifier. For instance, there is an important parameter that is called the steam to biomass ratio that is associated to the amount of steam that we put inside of the gasifier per unit of mass of the amount of carbon that is, or biomass in this case, that is entering the gasifier with the biomass. Then we also need to bear in mind that the biomass drying can consume a lot of energy that can be around 10 and 15% of the energy initially embodied in the biomass in a lower heating value basis. The biomass chipping is also a large consumer of power, and it's equivalent to 3% of the energy initially embodied in the biomass, again, as a lower heating value basis. The steam generation, along with the biomass drying and the preheating, can be partially supplied by cooling the flue gases and the syngas produced. Let's now discuss some details about the model and simulation of the gasification process. In the drying step, we are more interested in determining the amount of water that it has been removed. We know that there is a preliminary drying step outside of the gasifier, and there is also an internal drying process inside of the gasifier. Knowing the initial biomass moisture and the desired biomass moisture after the drying processes, as well as the mass flow rate of the wet biomass, we can determine how much is the amount of water that it has been removed in the drying process. Next, in the pyrolysis process, what we can see is that we need to use empirical correlations to determine two things. First, the fraction of gas, char, and tar in a mass basis, and dry biomass basis. This gas, in turn, it can be composed of different volatiles. In this case, we call it a gaseous volumetric fraction that we can also determine by empirical correlations. As you can see, it will provide the volumetric fraction of the carbon monoxide, the carbon dioxide, the methane, and the hydrogen that has been produced during the pyrolysis step, that, as you see, is following the drying process. Next, we have the reduction step. In this step, all of the gases that have been generated during the pyrolysis process, together with the gasifying agent, that in this case is the steam, are reacted in different sets of reactions, such as the methane reforming, the water gas shift reaction, the carbon drying reforming, and then other equations that are also going to produce condensable star, but in order to reflect the real composition of this reduction step, we need to adjust the approach to equilibrium temperature. There are some parameters that allow us to go closer to the reality, because we don't want to overestimate and underestimate the production of certain compounds, such as tar or methane. For that, we use this equilibrium, the approach to equilibrium temperatures, to shift the reactions further, so far from the equilibrium. And then in this way, by using data that is collected from the literature, we can get compositions of the syngas that are closer to the actual compositions. In this case, we use a steam mass flow that considers that the dried biomass requires 0.75 amount of water to gasify dry biomass. As we say in the combustion step, the char that is produced during the pyrolysis step is burned with air, more specifically with the oxygen that is in the air. In this case, the combustion generates a lot of waste heat because it's an exothermic reaction, and this heat is used to balance the endothermic enthalpies of reaction of the pyrolysis and the reduction steps, as well as for providing the heat for the internal drying. We assume that there is a complete combustion of the char using the air. Let's now talk about the biomass gasification in the context of the process integration. Here it's important to recognize which are the waste heat recovery potentials of the biomass gasification. We know that the biomass drying together with the gasifying steam requires at least 1,000 kilowatt hour per ton of dry wood, which is equivalent to 25% of the biomass energy in the lower heating value basis. The gasifying internal heating demands are balanced by the combustion of the char, and that amounts around 800 kilowatt hour per ton of dry wood. This heat is available at a temperature that is higher than 800 Celsius. The syngas and the flue gas cooling provide around 1,100 kilowatt hours per ton of dry wood of waste heat, that is above 100 degrees Celsius. The low-grade waste heat at lower temperature, around 80 degrees Celsius, and is more or less 1,000 kilowatt hours per ton of dry wood, can be used for a district heating network. Here in this diagram below, what we can see is that when the wood reference energy input into the gasifier is around 1,000 kilowatt, the amount of syngas that is produced is around 700 kilowatt. In this sense, the energy efficiency from syngas to wood is around 70%. We can also see that depending on the biomass that we use, we may have different demands of drying, but by drying, we will generate a hot stream that can contribute to the heat recovery system. In the case of chipping, we have a consumption of power for grinding and then controlling the size of the particles of the biomass that go to the gasification step. There, we know that we need to provide water in the form of steam, and then this steam is going to react with the gases that have been produced in the pyrolysis step. Afterwards, this gas needs to be treated. First, you will need to quench it by releasing a large amount of waste heat, and then it needs to be treated to remove the condensables, that are the tars and other heavy hydrocarbons that may be present in the syngas. In this cold cleaning, so the quenching and compression, we consume a certain amount of power, but then we also release a certain amount of waste heat. As we said before, the use of a separated combustion chamber is interesting because then we don't dilute the syngas that is produced with the flue gases, but the flue gases are also a source of waste heat that can contribute to the heat recovery system of the full gasification process. Here at the right, we see the composite curves of the gasification process. Then you can see that the hot streams are basically the flue gas and syngas cooling, the syngas intercooling in the compression, and the steam condensation, the steam that is embodied in the syngas, and the scrubbing water that heats when we are doing the quenching of the hot syngas. On the other hand, the cold streams are composed of the biomass drying, the steam generation for the gasification, and the air preheating for the combustion chamber. As we have described in the previous slide, the biomass gasification can generate partly the waste heat that it requires to preheat the streams that are fed to the gasifier and the steam that is generated for using it as a gasifying agent. But when we are going to produce also synthetic natural gas, then we need to take into account additional amount of waste heat that will be released in the autothermal reforming, in the water gas shift reaction. And then these two processes are required to adjust the ratio of hydrogen, carbon monoxide, and carbon dioxide, because we require a ratio that is around of 3 needed for the methanation reaction that is also called Sabatier reaction. The syngas conditioning releases waste heat above 300 degrees Celsius. This is partly used for the drying or preheating the process streams that go to the gasification unit. The physical absorption system that it comes after removes the CO2 that can be commercialized, sequestered, such as in mineralization or injection processes, or use it in a co-electrolysis unit to produce more fuel. The conditioning syngas is then finally reacted in 3 exothermic catalytic methanation beds. There we have intercooling because we want to increase the methane yield in the methanation. And then this waste heat that is normally about 300 degrees Celsius is also useful to contribute to the waste heat recovery system of the overall synthetic natural gas production. This is the diagram that shows the different sections. For instance, the syngas treatment and purification with autothermal reforming that sends the syngas, the raw syngas that has been conditioned and purified into the conditioning section that is where we remove the CO2 content. The CO2 content in this physical absorption system, it can be as high as 30%, and then depending on the ratio that is required for the methanation process, we need to reduce the amount of this CO2. As we say, it can be compressed and used for other purposes. In the methanation, the intercooling play a role that allows to first protect the catalyst, but also increase or shift the production of the methanation towards the equilibrium. Then in this slide, we present a summary of the streams, cold and hot streams, that are associated to the gasification and the methanation process. As you can see here, in the composite cores, there is a large amount of waste heat available at high temperature from the cooling of the flue gas and the syngas, as well as the methanator intercooling. The syngas intercooling, when we are compressing it, also supplies a useful amount of waste heat. The energy efficiency of the synthetic natural gas production is around 64%, meaning that we can produce around 2,400 kilowatt hours per ton of dry wood. The gasification, the water gas shift reaction, and the methanation can release waste heat below the 400 degrees Celsius of around 1,500 kilowatts per ton of dry wood. This is useful to generate steam used as gasifying agent, but also to preheat the gasifier streams. There is another amount of waste heat that is available at very high temperature, about 450 degrees Celsius, and this is around 700 kilowatt hours per ton of dry wood. The waste heat recovered at very low temperatures, below 100 degrees Celsius, that is around 700 kilowatt hours per ton of dry wood, can be capitalized in a district heating network. So in these curves, the composite curves and the grand composite curves, it's possible to see the amount of waste heat that is available at the different temperature levels. So we have seen that it's possible to determine the amount of waste heat recovery in the gasification process, but also in the gasification integrated with the methanation process for synthetic natural gas production. It's important maybe to know if there is an advantage of integrating this gasification and methanation system with other industrial processes, such as aluminum remelting. The aluminum remelting consumes a large amount of natural gas to supply the aluminum furnaces. But maybe we can replace this fossil natural gas with synthetic natural gas, then reducing the impact of this sector. But of course, we have less amount of biomass that is actually reported as available because the biomass have several other uses, such as the construction or even for heating households. Then, if we consider the amount of biomass that is available for the conversion and production into fuel and the use in the heavy industries, we can think that the treatment and the gasification of the biomass add some waste heat that can be useful to be integrated into the aluminum remelting plant. Also, if we consider then the upgrading of this syngas for using it directly in the aluminum furnaces, or the conversion into methane in a methanation process, because we can store methane, or we can use directly methane in the aluminum plant, then we are having a better use of this biomass energy at higher temperature. And then the low temperature, then we can use it, the waste heat at lower temperature, for providing the needs of a district heating network. Here we show a superstructure of all of the technologies that can be integrated so that they can supply the needs to aluminum cast house. We can think in the import of the electricity grid. We can import also natural gas grid. We can have a biomass market that can give us the biomass required for the gasification process. But the biomass can be also used in the wood boiler. And then the wood boiler, it can directly supply the heat, or it can supply energy to a steam cycle that can also generate power. On the other hand, the wood gasification, as we said, it can provide directly the syngas. It can provide the syngas to the syngas conditioning and methanation unit. And then in this sense, we can provide two types of fuels to aluminum remelting plant, the synthetic natural gas and the syngas. But then the CO2 that is produced can be also valorized by using an electrolysis and methanation unit that merges the CO2 that is produced in the aluminum cast house after we burn the synthetic natural gas to produce more fuel in a cyclic fashion. Also, we can use the waste heat that is available through all of the plant, gasification in the aluminum remelting plant, by generating power, by leveraging steam networks or supercritical CO2 power cycles. We also say that we can store synthetic natural gas or we can store CO2 because depending on the seasonality of the renewable electricity, we can decide to generate more or produce more synthetic natural gas by using the methanation if we store the CO2 during the winter when the electricity is not attractive to produce more methane. We can see also here that we can use different types of district heating. We can use groundwater heat pump, and then we also can use a water district heating network, so we call it CAD because it's chauffage at distance. Or we can also use a district heating network that is based in CO2. This everything to supply the energy needs of a city, a nearby city of the aluminum remelting plant. So as we can see, we can have several scenarios in which we can leverage gasification and methanation. We can also use wood combustion to directly provide heat or for cogeneration. We can have electrolysis that allows us to recover the CO2 and react it with hydrogen to produce more methane. We can have either water district heating networks or CO2 networks, and we can leverage also oxy-fuel furnaces. These for different scenarios that produce synthetic natural gas, that cogenerate using the waste heat available through all the plant and the gasification process. And we can also use boilers for cogeneration or even using oxy-combustion of the synthetic natural gas in the furnaces of the aluminum remelting plant. We can also leverage one technology that is called the power-to-gas system that takes the CO2 that is captured from the furnaces of the aluminum remelting or from the gasification process, and then it reacts with the hydrogen produced via an electrolyzer in order to produce more methane. So let's see some of the options that we have selected for comparing the use of the biomass either in the production of synthetic natural gas or the direct supply of the waste heat into the city. As we can see here in this plot, in which we have different options for using the biomass against the energy consumption, the total energy consumption considering biomass, natural gas, if there is any import of natural gas, and electricity. We see that when we produce synthetic natural gas, and we use also oxycombustion or normal combustion of this synthetic natural gas in the aluminum remelting plants, we can rid out of a large amount of fossil natural gas that needs to be imported in the case that we do not produce synthetic natural gas because we are using the biomass directly in a boiler. In this case, you can see that we can reduce the energy consumption by generating synthetic natural gas. Also, we see that if we produce synthetic natural gas, but then we cogenerate and then we also consider harvesting electricity in a power-to-gas system, we may have moderate increased consumption of electricity. But it's important to see that also we have the possibility of reducing the import of biomass compared with the other scenarios, because we are leveraging the availability of renewable electricity to produce fuel, instead of only using biomass to produce the synthetic natural gas. It's important also to see how by using the biomass in a rational way, it means by producing synthetic natural gas, we can reduce the amount of emissions of the overall system. Actually, we can have negative emissions when we produce synthetic natural gas and use it to drive the aluminum remelting furnaces. But when we use natural gas, because we are not using the biomass to produce synthetic natural gas, we have a very large amount of CO2, fossil CO2 emissions. Here it's important to realize that even by using the power-to-gas system, we can reduce the emissions compared to the business as usual scenario, that is using fossil natural gas in the aluminum plant. We have still a little bit of emissions because the electricity consumption carries with it some indirect emissions. Of course, if we are planning to integrate other energy technologies, such as the power-to-gas system, the oxy-combustion systems, or even the cogeneration systems, they are going to be more expensive, so the CapEx will be higher compared to the business as usual scenario. But of course, we need to take these results with care because they depend on the current prices and of the energy, like the biomass, the electricity, and the natural gas, and also because the investments, they are from the current states of the market. But in the future, these prices can reduce because of the economies of scale and the penetration of the renewable electricity. Let's then discuss about the integrated curves of the previous configurations, as well as other configurations for biomass utilization. As we have seen in the previous configuration, it was possible to use synthetic natural gas to fire the aluminum remelting furnaces. And then all of the waste heat that is available from the gasification, the methanation, and the aluminum furnace stack gases could be used to cogenerate power. The waste heat can be sent through a district heating network to the city. Then we also saw that if we use power-to-gas systems, then we can increase the electricity consumption and then reduce the consumption of a valuable renewable energy resource that is biomass. We can see also here from this table at the left that some of the configurations, such as the biomass boiler, in which we use directly the biomass to produce hot water instead of generating synthetic natural gas, requires the full import of electricity. We don't have cogeneration system. But also from this plot, we see that we still require the large amount of natural gas import to fire the aluminum remelting furnaces. For the composite corpse, it's possible to see that using biomass merely to produce hot water for the district heating is not the best option for using the high-grade energy embodied in this resource. For instance, biomass could be rather used to produce steam in a combined heat and power production unit, a Rankine cycle. And then with this, we are able to provide both the electricity and heat to the district heating network. In any case, for both of those cases, we need to import a large amount of natural gas because we are not producing synthetic natural gas that is required in the aluminum remelting furnace. In the other two cases, when we use the biomass to produce synthetic natural gas, we can use this natural gas for reading out the import of the fossil natural gas. And also, we can import a little bit more of electricity to balance the cogeneration electricity produced by the cogeneration systems, recovering the waste heat available through the gasification, the methanation, as well as the fluid gases of the combustion furnaces. So it's important to emphasize the profile of the integrated course of some selected configurations, especially those that are related to the biomass or synthetic natural gas production. Here we consider the furnace stack gases, the gasifier flue gas, the methanation intercooling are able to produce enough amount of waste heat that can be converted into power in a transcritical CO2 power cycle. This heat is also enough to produce the steam for the water gas shift reaction and the steam for the gasification. The fatal heat that comes out of this integrated system can be sent to the district heating network. We can also think in how it looks like when we change along the year the availability of electricity and biomass. In these two configurations here, we see that during the summer, the methanation is only used to produce fuel that is going to be used in the winter. But then in the winter, the electricity is not used to generate more methane because the electricity is more expensive. Then in that case, we just consume the amount of gas that has been stored in the methane storage tank, and the gasification system continues producing more fuel that is used in the overall system in the aluminum remelting, but as well in the district heating network. So we have learned in this presentation about the advantages of the biomass integrated gasification, the production of synthetic natural gas, as well as all of the parameters that govern the production of the syngas and the waste heat recovery through the gasification and the methanation plant. Also, we have analyzed the advantages of using the high-grade chemical energy of the biomass for supplying the heat and the power of an aluminum remelting plant and a district heating network. We know that by using biomass, by using process integration and a smart fuel and CO2 management system, also leveraging storage systems, we can reduce the energy consumption and also the emissions of the overall system. We can even reduce or make negative emissions when we operate the aluminum remelting plant, because the CO2 that is biogenic can be sequestered permanently by using mineralization or injection, then reducing the impact of the aluminum production. We know that district heating network should use only low-grade waste heat because the needs are very low temperature. Then also the utilization of heat pumps and the partial electrification may help reducing the consumption of the biomass and then prioritizing the biomass for other uses in the industry. Finally, we know that by using biomass, we find many challenges because biomass is used for other purposes, for construction, and also in other uses for the society. Then the best use of the biomass needs to be prioritized. And it means that even the waste heat that is released by its conversion, it needs to be used to generate other valuable resources, electricity in cogeneration systems or in the city as a way of supplying the domestic hot water and the space heating.